Hopefully this will make up for me running out of time in lecture 2. I finished the repeat of the second lecture on this slide, and I did possibly canter through this a little bit quickly in the original lecture at 10 o'clock on Friday, so it won't harm to start here. And I think perhaps we can analyse those graphs a little bit better as well. Excuse my email. So basically this was Keeling, who started to record data directly measuring CO2 in the atmosphere at Mauna Loa, the volcano in Hawaii. And he started collecting these data in 1958, and therefore we now have this record of real data. We've started collecting data obviously in other places in the world, and if you go onto the Scripps website you will see where they're currently collecting data, including Cape Grim in Tasmania. They need data a long way away from population centres, because then the air is well mixed and they're not looking at local perturbations, of course. Now, to look at this again, I suppose when I look at this graph I see really probably three key points here. But the first thing you do when you look at the graph is you look at the axes. So this is the time in years and we are here. So time is going that way along the graph, back into the 1950s, late 50s. CO2 concentration is in parts per million. So every million bits of air, whether that be grams or tons or whatever you want, would be out of those million bits of air, 310 of them, say, would be carbon dioxide, CO2. Or if you're, that would be back in 58, or if you were taking the measurement today, it would be 401. So in other words, we've gone up by about 80 ppm, or 70 or 80 ppm in the last 60 years. So we're going up by more than 1 ppm a year. Now, that brings me to my next point, which is one of my observations from this graph, which is that this is not a straight line, okay? There is a curve to this slope. So if I go through this, or you actually do this with a cursor, you can see that there is a curve interrupted here with a little blip. Now, another way of thinking about this is that if you were looking at the same rate of increase, and don't forget, rate of increase means the amount of CO2 you would go up in per year would stay the same, then that would give you a linear relationship. You would have a straight line. Okay, so if you went up 10 ppm per year, it would be 10 in year 1, 20 by year 2, 30 by year 3. It's a linear relationship. It's not a linear relationship. If you wanted to try and fit straight lines to this graph, you would probably get a reasonable line going through here with that sort of trajectory. Then you'd have to change and have another line going at this angle here, and then another line going at this angle here. And these lines are steepening. There is actually a bit of a blip here in the late 80s, early 90s, where it was even steeper and then sort of flattened out a bit, and then it started to take off again. And this means that the rate of increase is increasing with time. And so you could divide this up into, say, this slope here, and that slope there, and then this slope here. And you could say, therefore, that over the last, since 2000, the rate of increase per year has been higher than it was between that period and 75, and that was higher than that period there, 58 to 75. So indeed, the rate at which CO2 in the atmosphere has increased is in itself increasing. And this leads to a curve, which, as we will see in the next graph, is actually exponential. It's doubling effectively. Now, you can also see on here that there is an increase. It's not like we've got data that are going up and down and stable and then up again and then down and stable. This is an increase. Nowhere is there any fluctuation in the data here that's greater than about 3 or 4 ppm. Okay, but the thing about these cycles is that they only last a year. Each cycle lasts a year, and you go from a bottom to a peak, so a minimum to a maximum to a minimum. But each maximum is higher than the previous one, and each minimum is higher than the previous one. So we are going up. Okay, and as somebody excellently volunteered in the last lecture, this is the Northern Hemisphere forests breathing effectively, deciduous forests in the landmasses in the high latitudes in the Northern Hemisphere. When they get to winter time, they shed their leaves. Not a common occurrence in Western Australia. And when they get rid of their leaves, that's a very large tonnage of organic matter that is being shed and then decomposes. And as it decomposes, the carbon dioxide in the leaf is released into the atmosphere. Stays in there all winter, so these highs are the winter in the Northern Hemisphere, and then as the trees start to grow new leaves, which is the end of the spring, which may be April, May time, depending on where you are, then they grow very quickly and they draw down CO2. And so this base area here will be the late spring, early summer, where the leaves are fully grown, all the new leaves are on the trees basically, and you've actually storing carbon for a few months of the year. You're drawing it down out of the atmosphere and you're storing it in those leaves, but which then release it when they decompose. So you're seeing this cycle repeated, which is nice because it ties in with what we know happens, and it makes you start to think, these data are real data. There's no glitch here. Now, there is an increase, and this isn't a vague increase, it's a very definite increase. 2, we see these seasonal variations, which are repetitive and rhythmical. And 3, the rate of increase is increasing. Okay. Next graph is the slightly longer short time scale. So we have our last 60 years or so of data here, since 58, and to here. This, as you can see, this very steep rise now on this scale, and the preceding 250 years going this way. Okay, so these are the only data that are measured directly from the atmosphere. These are data that are proxy data that were measured in other forms, right? It's ice core data here, but these data are very, very rare, and the resolution, as you can see, is not perfect. You don't have as many data points here. Now, so in the period between 1700 and maybe 1800, there was very little increase. It was almost like a baseline, almost flat. And then you start to take off in the 1800s and then climb with a vengeance, If you interrogate these data, you will see that the period after the wars, or during the wars, the World War I and World War II especially, there's actually a reduction in the amount of CO2 in the atmosphere because industry virtually ground to a standstill during those periods. You can see the wars in here, okay? However, you then start to go on this amazingly upward trend, and this now starts to look even more like an exponential curve. So you're starting off flat, you start to increase very, very slightly, and then you go sky high. And indeed, the natural result would be to become almost vertical. So you will be increasing CO2 concentration very rapidly year on year. You'd be getting to on the order of 5 ppm a year fairly soon in this sort of curve, which is the worrying thing, i.e. it's a runaway type of process, okay? Now, the next graph goes back 800,000 years, so we're here at t equals 0, and that's 800,000 years in the past, or 800 Ka. K stands for 1,000 A for annum. Same parts per million CO2 concentration. And the immediate thing you can see is that there is no other recorded data showing anywhere near as high. So we're at 400, just over, and really the tops of these maxima are at about, 270, 280? So at the moment we're standing proudly about 120 ppm higher than the record CO2 concentration in the atmosphere over the past 800,000 years, which is pretty specky. Now, you can see that there are cycles in these data, but they're not, as perfect as your seasonal cycles, but there is this sinuous appearance. And you can virtually say, okay, we've got maxima, jaggedy, minima, maxima, minima, yeah, okay, you're doing this. And you can say, right, there's one cycle. If you measure from minima to minima, or minimum to minimum, 1, 2, 3, 4, 5, 6, 7, 8, and we're into the 9th in the last 800,000 years, which means that these cycles last for slightly less than 100,000 years, maybe on the order of 95,000 years or something. But again, we have gone way out of this cycle. Now that means two things. One, you take what you see, and that means that we haven't reached 401 ppm CO2 in the atmosphere on this planet in the last 800,000 years. It could also mean that we are starting another cycle, but it's a long one. I.e., for all we know, and this is an argument against CO2 being totally anthropogenic, so to speak, or at least this bit being anthropogenic, is that there may be a cycle back here somewhere, which we haven't got the data for, where on the maximum, say even before this one, the data, actually the CO2 concentration went up to here, because then we'd be looking at almost 1 million years between cycles. Now this could be the case. There could be a natural cycle that caused peaking in CO2 every 1 million years. But that's almost by the by, because we weren't around then. We certainly weren't around in this form. And, it is going to affect us. There is no doubt about that. So the problem here is how much of the CO2 is anthropogenic, is related to us. And indeed, it is related to us because nearly all of this, we can fingerprint it isotopically, and it comes from the burning of fossil fuels, long-term carbon storage, and we've interrupted that. We've opened that locked storage system and we've released that CO2. A lot of it has been brought out of long-term storage and thrown back into the atmosphere very quickly. Faster than the Earth has managed to do over the last 800,000 years. So as I say, that's a way to interpret this. This site is excellent. Have a look at this site. Now we come to Milankovitch. We've been looking at CO2 as a component that seems to mirror ice ages. Okay, I'm sorry, I didn't mention that. These minima are when ice ages occur. Okay, so here's the maximum glaciation in the glacial ice sheet maximum, which was about 25,000 years ago, 26,000 years ago. And that's where CO2 is the lowest. As we come out of an ice age, not an ice age, but of a peak glaciation period, then you'll see there's always a very sharp rise in CO2 due to the increased global temperatures. Okay, and indeed, it is noticeable that it is a very sharp rise, whereas the decline into a more glacial, a bigger glacial period is often a bit uppy and downy. Okay, so it's always this left-hand side where we're coming out of major glacial coverage and going warmer, and then a bit of windrilling about, and then going cooler, and then warmer. Okay, it's always steep, warmer. So related to temperature, effectively. Next one is Milankovitch. Milankovitch cycles. Go to this website. I'm not linking to it here because it would be too complicated in this form of recording. And they will show you that there are major cycles that the Earth goes through in the distance it is from the Sun, i.e. how eccentric or non-circular the Earth's orbit is around the Sun, the angle at which the Earth is tilted from the poles, the obliquity, and the way in which, if you were to put a line through the poles, this processes around a circle. All of these are equally important, really, but they have different effects on either the amount of solar radiation that we receive and when we receive it, with the continental landmasses in this configuration. And that's important. So some of these cycles particularly affect seasonality in, say, the Northern Hemisphere. So they will make winter time, the difference between winter and summer temperatures, greater or less, depending upon whereabouts in these cycles we are. And also these cycles occur at different intervals. So you have some cycles are about 20,000 years, and some are the bigger cycles, which are around 100,000 years. And so one cycle is going up and down while we're slowly progressing through another one. So that complicates it. And every now and again, they'll all be in phase. But most of the time, you'll get one cycle will almost buffer another cycle as far as effects go on the Earth. Okay, do have a look at Milankovitch. They are spectacularly interesting, and you can really see Milankovitch cycles. You are looking at Milankovitch cycles here. Okay, and that's the summary. All right, I hope that has helped you a little bit.